Hello math friends, this is section 4.2 notes for pre-calculus. Today we are going to be talking about logarithmic functions. Yesterday in section 4.1 it was exponential functions. A logarithm is an exponent, so it makes sense that we discuss these two things in the same chapter. Logarithms and exponential functions are inverses of each other. So reflections over the line y equals x, right? So if the exponential function is f of x equals a to the x power, then the inverse of that would be f of x equals log base a of x. You should remember this definition from Algebra 2. Log base a of x equals y, that's log form. So then the base of the log, a, becomes the base of the exponent. The exponent is on the other side of the equal sign, so that's your y. And then that is going to be equal to what's inside the log, which is x. And of course, where a must be greater than 0 and a cannot equal 1. Because if a is 1, then again, 1 to any power is always just 1, right? So we would never have any change in our function. Okay, so the first thing we're going to do is just a little review practice of changing form, because this is a critical skill that you need when you're working with exponents and logs to be able to go back and forth from form to form. So in our first example, we have log base 5 of 125 equals 3. If we want to write that in exponential form, the base of the log, which is 5, is where we begin. Begin with the base. So the base of our exponent is 5. The exponent is always what the log is equal to, so 3. And then the exponent is equal to what's inside the log. And the ones that have numbers like this are always nice, because in exponential form it should be easy for you to check. 5 cubed equals 125. Yes, I know that that's true. Okay, our second example, we have exponential form and we want to go to logarithmic form. Okay, again, begin with the base. So the base of our exponent here is 12. That's going to be the base of our log. So we're going to write log base 12. And then I'm going to put my equal sign down. Now we know that in log form, the exponent is always on the other side of the equal sign. So our exponent in exponential form is -2. So I know that has to go on the other side of the equal sign, which means that 1 over 144 must be what's inside the log. And then my last example, again, going from log form to exponential form, begin with the base. The base of the log is 7, so the base of the exponent will be 7. My exponent is p, and 7 to the p power will be equal to k. All right. In the next examples, we're going to be evaluating some logarithms. Notice that it says here, without a calculator. These are brain power problems. So what you want to do is think about this in exponential form. Log base 9 of 729, what is that equal to? Well, basically what we're asking is the base, which is 9. We're trying to figure out the exponent, right? So 9 to what power is 729? Well, we know that 9 cubed is 729, which means that log base 9 of 729 is equal to 3. In my next example, log base 2 of 0.125 is what we're trying to evaluate. So we know our base is 2. Again, we're trying to figure out the exponent. 2 to what power gives us a value of 0.125. Well, if you're familiar with fraction decimal conversions, hopefully you know that 0.125 is equivalent to 1/8. So if you think about this, we're taking 2 and we're turning it into a fraction. So you have to think about what kinds of exponents turn numbers into fractions. What kinds of exponents move things downstairs? Those are our negative exponents. Negative exponents make fractions. Okay, so that's our little reminder. So basically, we just have to figure out 2 to what power is 8 and then make it negative. Well, 2 to the third power is 8. So 2 to the negative 3 power would make 1/8. So that tells us this logarithm is equivalent to negative 3. And then the last one, this is an interesting one as well. Our base is 64. We're trying to figure out what exponent on 64 would turn 64 into 8. Okay, so what kind of exponent? Now it's not turning it into a fraction, so it's not going to be negative, but it's making a bigger base into a smaller number. Okay, so that means that in this case, our exponent must be a fraction or a root. So 64, what root of 64 is 8? Well, the square root of 64 is 8. And as an exponent, a square root is a 1/2 power. 64 to the 1/2 power is 8, right? This is really saying this square root of 64 equals 8. So that means that this logarithm is equivalent to 1/2. We have our properties of logarithms, and again, these should be familiar to you. Log base a of 1 equals 0, because if we change to an exponential equation, then we would get a to the 0 power is 1, which we know is always true, right? Any number to the 0 power is 1. Log base a of a equals 1, because if we change to an exponential equation, we would get a to the first power equals a, which is always true. Log base a of a to the x power would equal x, because if we change to an exponential equation, we would get a to the x equals a to the x. So that's a true statement. Whenever the base of your log and the number inside of your log are the same, basically they're going to undo each other. And then this next one is kind of the inverse of the previous one. If we have a to the log base a of x power equal to x, if we change this to a logarithmic equation, then we would get log, the base of our exponent is a, so log base a of x is equal to the exponent, log base a of x, which is a true statement as well. So using these properties of logarithms, let's do a little simplifying of the following examples. Log base 7 of 7, okay, that's the second property up there. We know that that's going to equal 1, and if you want to think about it as an exponent, that's because 7 to what power equals 7? To the first power. My second example, log base 11 of 11 to the 5th, as an exponent, that means, 11 to what power is going to equal 11 to the 5th? Well, 5, right? We know it's got to be the 5th power. 72 to the log base 72 of 6. If we change that to logarithmic form, it's going to be log base 72 of x has to be equal to log base 72 of 6. So that tells us that has to equal 6. Usually when we get an example like this, we just take the shortcut, cross those out, and say they undo each other, so our answer is 6. The previous example is the same way. Log base 11 of 11 just cancels, and what we're left with is 5. But the proof is what I wrote underneath. And then the last example, 8 to what power equals 1? Well, anything to the 0 power equals 1. So that's going to be equivalent to 0. Next thing we're going to talk about is graphing a logarithmic equation. Standard form of a logarithmic function looks like f of x equals log base a of x minus h plus k. Okay, so this includes our shifts. Our parent function is just f of x equals log base a. I don't really have anything for you to put here under characteristics of a logarithmic graph, other than I suppose you could say that it's the inverse of an exponential curve. And we'll talk about that more in a minute when we make our graph. The domain of a logarithmic function is going to be x is greater than 0, or from 0 to infinity, and our range is going to be y equals all reals, or negative infinity to infinity. Hopefully that makes sense to you, because If exponents and logs are inverses of each other, then the domain and range of exponents become the range and domain of inverses. They flip-flop. For exponential functions, our domain was all reals. Now for logarithmic, our range is all reals, right? It's that inverse relationship there. And for exponential functions, we had a horizontal asymptote at y equals 0. For logarithmic functions, we are going to have a vertical asymptote at x equals 0. Okay. So the example that we want to graph here is going to be y equals log base 2 of x. So the easiest way to graph a log function is to change the equation to exponential form. That's easy to do. 2 to the y power equals x. So now if I'm going to graph this, it makes sense if I plug my y values into my table first, if I choose those, and then I plug the y values in to get the x values, because it's easier to work with this equation in exponential form than it is in logarithmic form. So I'm going to choose my fav 5, but I'm going to choose them as my y values. So -2, -1, 0, 1, and 2. And when I plug these in, 2 to the -2 will be 1/4, 2 to the -1 is 1/2, 2 to the 0 is 1, 2 to the first is 2, and 2 squared is 4. So when I will graph these, x is 1/4, y is -2. X is 1/2, y is -1. X is 1, y is 0. X is 2, y is 1. And x is 4, y is 2. So there's the graph of my log function. And I have, I'm going to try to make it a little skinnier here, I have a vertical asymptote right here on my x-axis. There it is. Okay. Now it says underneath the graph, also, graph y equals 2 to the x on the grid above. Well, we graphed that one probably like 4 times in the previous section of notes, so I should be able to reproduce that graph pretty quickly. And remember, it has points -2, 1/4, -1, 1/2, 0, 1, 1, 2, and 2, 4. So this is the graph of y equals 2 to the x power. This is the graph of y equals log base 2 of x. And these two graphs are inverses. They are reflections of each other over the line y equals x. So I could go ahead and I could add in that line y equals x right here, that mirror line, and you can see if you tilt your paper that these two functions are mirror images of each other over that line y equals x. Of course, just like with exponential functions, we can have shifts and transformations with our logarithmic functions as well. The first practice example we're going to do has a k value, right? This right here is a k value of 3, which means that we are going to shift our graph up 3. Since the base of our log is 2, okay, we're looking at the parent here. And the parent graph again is just y equals log base 2 of x. So I am going to think of this as 2 to the y power equals x. And I'm going to plug in y values. Now I just did this on the previous screen. So I'm going to go ahead and I'm going to reproduce that graph. It was 1/4, -2, 1/2, -1, 1, 0, 2, 1, and 4, 2, right? That's my parent graph, y, 2 to the y. Sorry, I have a little typo here. 2 to the y equals x. And you're plugging in your y values. Well, now if I'm going to be shifting my points up 3 to make my final graph, now I just have to move each of those parent points up 3. So 1, 2, 3, 1, 2, 3, 2, 3, 2, 3. So there's my